Hello, everyone. I'm Will Carr, and this is panel 3. We're here to talk about how TEEs, FHE, MPCs, and ZKs fit into the quantum world. If you don't know what those acronyms stand for, that's okay, because we're going to learn about it today. So, as you guys can see, we have a very large panel, and all of these people are experts in their own right, in their own field, and excited to just get into some conversation today. So I think we have 30 minutes. So to start, let's just kind of, everyone wants to kind of introduce themselves and talk about, a little bit about your expertise, and then we can get into conversation. If we want to start here, go for it.
Yeah, so hi everyone, happy to be here. I'm Bobbin, co-founder of Miden. Miden is a privacy-focused L2, and we use zero-knowledge proofs, specifically Starks, for privacy and succinctness as well. And I've been working on ZK stuff for about 8 years now, although I'm not a PhD in cryptography or anything of that sort.
Hi, I'm Ravital. I founded Sunscreen. We work on FHE. My background is entirely in lattice-based cryptography.
Hey everyone, happy to be here. My name's Renee. I'm the CEO and founder of OpenMatter. We do MPC for agent-to-agent interaction, and super happy to be here.
Hey everyone, my name is Ekleen Kaur. I am a software development engineer at AWS. I am also the founder of the Gator Blockchain Lab at the University of Florida. Brian on panel 2 was one of the folks that represented Algorand Foundation and also funded our labs. So started a lot of fun research work in blockchain space. So currently right now I'm open source developer in blockchain community. So I do have an expertise in ZK systems and cryptography.
GM, happy Quantum Summit. I'm Jake. We're building Zero Gravity. It's a stack to bring AI on chain and verifiable. It comprises of a layer 1 blockchain, a decentralized storage solution and network, decentralized compute layer, and a decentralized data availability layer. And we're working with a lot of great partners to bring trusted execution environments, ZKML, OPML, to a lot of these user experiences, right? So for storage and compute, we're running today with trusted execution environments, and we're working with Tectonic to make sure that we are post-quantum audited and working towards that future.
Hi everyone, I'm Remi. I'm the founder of Inco. We're a privacy layer for existing blockchains, and we've built with using all these acronyms before, so super happy to dive deeper into that. The first product we're going to launch is actually fully TE-based.
Hey everyone, Scott Dykstra, co-founder of Space and Time. Space and Time is a ZK-proven system that allows smart contracts to access data. We ZK-prove SQL on-chain. And so a lot of our work is figuring out what that looks like in a post-quantum world as well. Since we're at an improv show, I'll just give one quick dad joke. Why did the quantum computing company keep moving their headquarters? Because they couldn't pick a state.
Is that a Palantir joke right now with how they just left Colorado? Well, hey, I got a question. Does anyone in the audience not know like what TEE, FHE, what these acronyms stand for? Can I see a show of hands if anyone? Okay, so for the most part we do. Does anyone just kind of want to really briefly go over what these acronyms are?
Thank you, Scott. Yeah, I'll do this really simply. So we'll start with trusted execution environments. This is a way to achieve verifiable compute. You can think of this as using trusted hardware to prove on secret data. Then you have ZK, obviously zero knowledge proofs. This is sort of for single player privacy where you have a prover and a verifier and you're trying to convince the verifier that something is correct without revealing the raw information. And then you can kind of think of that as like you're verifying secrets is what the TE and ZK systems allow you to do. And then you have MPC, which is for collaborative computing. So this is where you collaborate on secret data. And this is another way to achieve verifiable compute in sort of a multiplayer privacy setting. And then the last is fully homomorphic encryption, which is really exciting to see it starting to scale over the last like 5 years, I would say. And that is just fully arbitrary computations on encrypted data.
Yeah, so another open question to the panel. So of all those things, as quantum computing advances, is there one that is more subject to being compromised than any of the others?
I would definitely say TEEs are in the trickiest position. There is a physical hardware component, and it makes upgrading it a little bit more difficult. So I would be a bit concerned if you're relying entirely on TEEs for the next 3 to 5 years.
And I assume that would be fairly expensive to have to upgrade that hardware.
I don't know I'd be as concerned about like the cost, at least from like the blockchain perspective. I suppose if you're the manufacturer, maybe there's a problem, but I'd be more concerned about how long it's going to take to roll out the upgrade.
So from a post-quantum perspective, I would say T's are fine. And the reason why they are secured by hardware, right? So you cannot really break hardware with math, right? The interesting thing is 90% of all the privacy protocols out there are actually not post-quantum secure, not because of the signatures, but because of the privacy. And so from a ZK perspective, most privacy projects use elliptic curves for encrypting things, right? So that is actually very problematic because one day you'll be able to decrypt these things because all these data are actually on chain and blockchains are immutable, right? So it's like a permanent storage layer, right? I would say MPC is also have similar problems here. I think FHE is the only thing that's actually post-quantum secured directly. But with TEs, what you could do is use symmetric key encryptions, right? AES, polychacha. So these are also post-quantum secure from a cryptography perspective. Yeah.
I would say there's like some parts of TEs that are beyond just symmetric key cryptography, but I don't disagree in the sense that they are not in like the worst position, but they aren't necessarily using hash-based or lattice-based cryptography, which is very well understood in a post-quantum setting today.
Yeah, that's fair. Yeah, within the T, you could, some of these signatures, we will probably want to upgrade that.
I also, just not to be controversial here, but we have had like 2 or 3 known hacks from both Amazon and NVIDIA TEs this last year. You can go to te.hack and read about it, but you don't hear about that with like ZK or MPC really. I think as long as you're using lattice-based cryptography, you're preparing yourself for a post-quantum world.
I kind of disagree with that, to make it a little bit more controversial. So TEs, yes, it's a physical hardware securing physical secret, right? You need to have access to the hardware to be able to attack it, right? So if you run this behind like a large data center like Google Cloud or Nitro, these are heavily guarded data centers and also hidden around the world. So good luck like breaking them, right?
Sure, yeah. It's a fortress for your data, but fortresses are meant to be broken into. I guess it comes down to fundamentally like, do you want to trust the math to secure it or do you want to trust the hardware to secure it? And I tend to trust math because I think ultimately really well-designed software is harder to penetrate than hardware.
I agree long-term, yes. However, even ZK is not technically production ready, right? There's still bugs for the next 1 or 2 years. So is it really more secure than something that exists for a long time already? And then we know works. And institutions are already using it, right? Banks, hospital, and everything. So I would say it depends on the time frame. Especially on the post-quantum security side, I think that also matters, right? What cryptography you're using. And
I think one thing to think about, say about ZKP specifically, like I agree with Remi that a lot of the current protocols do use, elliptic curves that are susceptible. We do have ZKPs like hash-based, ZKPs, lattice-based that are also coming into, like, there's a lot of research happening. So there's a very clear path of how ZKPs can move to post-quantum. And I think some projects are fairly well positioned, but there is most of the projects right now, I wouldn't know if most, but a lot of the projects are using non-post-quantum cryptography, and ability to migrate a specific project is maybe be more difficult for some projects than the others. For example, I have no doubt that Zcash guys will migrate to post-quantum cryptography in a fairly timely manner. Some other projects, I'm not so convinced.
Well, when it comes to all these different approaches, like which, I guess my question would be like, which, from an actual consumer, like, you know, it's easy for so many, you guys are so technical, like all of you guys have so much technical expertise. Sorry, I'm waving my hand right in front of your face. But from a general consumer standpoint, like which one of these is actually going to affect the lives of the everyday person the most? Do you want to take this, Ekleen?
So here's my opinion. So what's primitive to the foundation of post-quantum world, in my opinion, is zero knowledge proofs. And particularly like transparent, secure ZK systems, not T's, because post-quantum does not care about like side channels attack or microarchitectural leakages or governance capture, not MPC, because yeah, great. They build threshold trust and they are a great key distribution management system between anonymous identities on the network. But when we talk about quantum security, we care about not building it upon trust assumptions, like discrete logarithmic problem that MPC so strongly assumes, and also a trusted setup. So now coming back to formal homomorphic, fully homomorphic encryptions, right? So even though FHEs can be built in isolation, but they are arbitrary computation that guarantee privacy. So privacy in computation versus verifiable correctness. What really presumes in blockchain foundation when I'm building a proof system? So like the answer is out there. When I am designing a proof system, I want it first to be verifiably correct, and then I want to ensure security and the added constraints around it. So essentially, why ZK dominates in this post-quantum context? It's because quantum adversaries threaten discrete logarithmic assumptions that are now broken by Shor's algorithm. We talked about it in panel 1, panel 2, and also the presentation by Tectonic Labs that also briefly went over Shor's algorithm. Second, ECDSA, BLS signatures. Third, arithmetic circuits like Groth16, KCG, or commitment schemes. So all of our foundational cryptography that is currently surrounding all the blockchain ecosystems is already jeopardized under the lens of post-quantum security and post-quantum adversaries. But so I just said ZK is my like primitive foundation when I'm standing on the standpoint of post-quantum security. It's because despite these trade-offs, ZK is not a single primitive. It's a proof system that can easily swap the cryptographic primitives underneath. So this adaptability is what really makes it future-proof. That's my thing.
Interesting. Yeah. Anyone want to comment on?
I'm probably alone on this, but after really diving into the implementation of ZK systems, I'm a little bearish on ZK actually, mainly because of prover size. We were looking into some post-quantum secure symmetric key-based ZK systems. Maybe you've heard of it, ZK-BOO, and it's it's like 20 or 30 times faster than Snark's post-quantum safe. It sounded great. If you prove on just 1 megabyte of data, the proof size was like 3.5 gigs. And that doesn't scale for enterprises, right? So I think for me, what's interesting, and also what's interesting about ZK is I think out of all 4 of the sort of privacy primitives, MPC is understood the least in the community. Maybe that's because it's got a lot of assumptions that you have to work out. But what's funny is like ZK, you can conceptualize ZK as a 2-party computation, like it's a 2PC, which is MPC. So I think MPC is actually going to be foundational to a lot of privacy primitives. I think distributed key generation, having ways for agents to manage interactions on chain without having full access to your private key is going to be like really seminal technology. I would say where ZK is going to be really good is with low entropy data and like smaller data sets. So like ZK identity, proving a passport verification, things like that, or agent identity, proving that you're an agent. Yeah, like for mass scale enterprise analytics, I don't know if ZK is gonna pull it off.
I somewhat disagree. Maybe with that proving system, yes, but for Starks specifically, like the proof sizes are, logarithmic in the amount of computation. So you usually
time takes hours though.
It depends on it depends what you're needing. Yeah,
it takes hours.
It depends what you're trying to prove, right? Like for blockchain applications specifically, you're rarely proving gigabytes of data in a single transaction. You're probably a transaction. So I agree with you that I don't know if you need, I don't know, there may be other techniques that people will come up with for large scale computations when you have gigabytes of data input. But I think for blockchain specific stuff, I think ZK should be pretty safe in the post-quantum world. Coming back to your question, I think I want to say there's that different tools. They have different applications in different places. I think they have uses, ZK has its use, FHE has its use, TE, MPC, all of them will be used in different ways. I have a bias toward ZK because this is what I'm working with. I do think there is one interesting property of ZK that others are can't emulate as easily. Specifically in a blockchain context, there are really three ways you can put data on chain. You can put in plain text. This is what most transparent chains do. You can put encrypted data on chain. This is what some blockchains do, and you would do the same in the context of FHE, for example. Or you can put just commitments to the data on chain, where only the hash of the data goes on chain. And in my mind, in the long term, this is one of the most secure ways to put data on chain, where you actually don't put the actual data on chain. The users or the relevant entities hold the data, and they can share it in different ways, but the chain itself never has the full data. And this is one of the ways you can achieve that property with ZK. I'm not sure about other constructions.
So to add on that, I heard one opinion that MPC is ZK is indirectly MPC because it involves a prover and a verifier. Earlier you said that you believe mathematical completeness over a hardware setup. So this is what foundational zero knowledge proof systems can really overrule. It doesn't matter how the system is built, as long as the underlying arithmetic circuits, the commitments can be quantum secure. So currently, Ethereum is actually using commitments to their parent block to replace their parent nodes that allows them to have no limit to how many children that they can have in their block storage layer. And that essentially means that in just a 4-level deep Merkle tree, I can consume all the Ethereum's live addresses that are present in the mainnet today. And this adaptability is because ZK's math is quantum secure or can be pivoted towards quantum security. And that's not something multi-party computations can ever give us, precisely because of relying on discrete logarithmic problems. So unless we are ready to build MPCs over lattice-based cryptography, or have fast read Solomon interactive proof of proximity, or over polynomial IOPs, or IPA over Brandestad's curves, then we can talk about, yes, MPC, holds the ground.
So our entire MPC protocol is lattice-based cryptography. We assume learning with errors over finite rings and use polyrhythmic fields for it.
So as long as to the point, if you're not using DL, that means you're post-quantum secure.
Yeah.
But that's essentially not the case for most MPCs right now. So that's just
very different.
Yes.
I don't know. I know of only one MPC protocol that claims to be post-quantum secure, and they're on Solana. And they handle, I think they require a trusted dealer, which we do not. So happy to share the white paper after the call or after the talk.
Ooh. Anything from the far side of the panel?
So all the things we mentioned, right? T, FHE, ZK, MPC, ultimately you can mix and match, right? What you want to know is how this is designed, and you want to think from two perspectives, right? Is the cryptography post-quantum secure? Can I actually break this in the future? And second, like Bobbin mentioned, where is it stored, right? The attack really is called harvest not decrypt later. I'm sure people have heard of this by now. The problem with blockchain is like if you store on the blockchain, you can decrypt forever, right? You can harvest forever. And you cannot retroactively change the history in the past as well, right? So this is where, yeah, if you do store, let's say, FHE on chain, it's probably fine because it's unbreakable, right? With post-quantum security. If you store things like symmetrically encrypted ciphertext, it's probably also fine. Now, if you start using things that are breakable on chain, this is where it becomes problematic, right? So I think really the way to think about this is this decryptable in the future, and where is the data stored? And typically in Web 2, it's stored behind like a server. So technically it's less risk because down the line, they can also like try to upgrade this down the line. But because Web 3 is a little bit more unique, everything is permanent. This is where whatever decision you make today for your privacy protocol, you're essentially freezing that choice in time forever. So this is why privacy is actually post-quantum security is important for privacy on day one and today, right? And not sometime in the future, which is a little bit different than like signature schemes, that actually do have time to be upgraded.
Yeah. Well, our next panel is on privacy, so we're gonna really dive into privacy here in the next hour. But as far as the topics that we're discussing now, what would the panel say is maybe some of the most overused? Like, what's some of the stuff that as we move into quantum, are any of these tools, will they somewhat become irrelevant in any way, or will they all remain equally viable and important?
One thing that I think none of us have mentioned in this talk so far is I really believe that there is a dire need to create testnets that are post-quantum secure and that are like readily available to all developers, not just high-power computations or companies, because that really is what transforms the movement towards everyone's thought process. Because if I cannot test it, how can I even guarantee quantum security or even claim quantum security? And this infrastructure cost is a lot. So yeah, I mean, it's not a single party effort, in my opinion. It requires more than just one organization that's trying to commit to quantum security.
I think that the market pits these things against each other. But if you talk to any real cryptographer and you say, hey, what's the holy trinity of privacy? They say ZK, MPC, at FHE. And it's a Venn diagram. And I think that all of these tools will be relevant in the future. They're just going to have different use cases. And I think as builders, we need to realize what those use cases are and make sure that they're complementary and we're not being combative towards other privacy protocols just because they're approaching it a different way.
Yeah, I was going to say something similar, that the Venn diagram of FHE, MPC, ZK is interesting. Just to add to what Ren said. So I think a lot of people get confused about like encrypting things versus proving things. And it's something you mentioned as well. And generally you need to do both for an end-to-end system to work, like a blockchain or a ZK proven, a prover that verifies on chain. And the problem becomes when you start swapping out the curves used for proving to new post-quantum curves that maybe get too large in size, then your proving times get longer. Or you want to keep those small and you start using new encryption methods to encrypt, let's say, hashes of data that are inputs to your ZK system. So you have like data that you need to hash, you have data you need to encrypt. You have computations you need to prove, and often you need to verify based on a key all the way back down the chain from the input data. So you have input data you need to encrypt, and then all the way down at the verifier, you need to decrypt or verify a signature. And so what you're always combining is like a better way to encrypt data at the start, or encrypt a hash of the data, or sign a hash of the data using a better curve. Then you need to prove some computation or hide some computation. Often that looks very similar, proving and hiding, same kind of ZK methodologies, but different math. And then at the end, you need to verify it. And that often requires verifying a signature or decrypting something. And so you're combining all these technologies, and maybe like MPC creates a much better way and an easier way to swap out post-quantum curves for encrypting hash at the beginning. But maybe like, data could be hidden via TEE as well at the beginning. So it's always kind of a combination of these three tools, or often four tools in a Venn diagram. And people always mix up hiding things versus proving things. Like space and time isn't so much a privacy system. We're proving that SQL was done correctly on often hidden data. We're proving computations, not trying to hide computations, where other teams are hiding and proving. So just to add to what Ren's saying.
For our approach to incorporating a lot of these new techniques, we, of course, worked with Tectonic to audit a lot of the protocol that we've built today. And there was about 10 line items that were actionable, right? Going through this, implementing that, of course, the Venn diagrams, I completely agree. Having multiple solutions is necessary, and we're agnostic to those solutions based on the certain use case that the user has around compute, around storage. And maybe for the experts here in the audience, I'd like to kind of think through how implementing these line items might even impose their own vulnerabilities. You'll have this, technique. It needs to be integrated. Of course, our tech team needs to do that. Do we need to think about the ways that there might be bugs in just getting to a post-quantum resistant kind of tech stack with our builders, with our devs? And maybe if you guys have any tips or tricks for the teams that are building out here, trying to be post-quantum, that'd be a great way to kind of lead with next steps for the group. Anyone here?
So this is why we were launching with TEs first. And yes, TEs are not perfect. And we can all agree it's a short-term solution, right? But the short term is 3 years, 5 years, 10 years, right? Until we get ZK that's post-quantum secure with encryption, et cetera, right? This is also why we decided to use something that has existed for a long period of time. The cryptographies that we use also have existed for a long period of time as well, like AES, Polychacha, et cetera. That's, I would say, you're basically reducing the risk on the newer cryptography side. And you're trying to maximize something that works today and is scalable today. And again, I agree that this is short-term solution, but we don't have a clear timeline of how long it's going to take for all these new cryptographies techniques to be time battle tested, right? Scalable. There's a bunch of these other things that basically the real world needs to consider, especially enterprise, because this is about basically, their time horizon is a lot longer, right? So this is about compliance, basically fiduciary duty, and they have to think about all the potential risks that could happen with some of these newer cryptographies. So, so I guess my suggestion is maybe think of different timelines and start with something that maybe works really well today, and over time upgrade to other things. Yeah.
Yeah. Or go ahead. Go ahead if you have a comment.
I am a strong advocate of ZK systems, but without trusted setups, precisely because I believe that quantum security has a lot of underlying problems to solve, such as scalability, hardware cost of computation. And yes, taking away a trusted setup also jeopardizes a lot of prover time and verification time. It requires a much more expensive, mathematically secure hardware. But having a system that's built around trust, that at least one person is an honest party and is discarding the toxic waste in the ceremony is a concern, in my opinion, especially post-quantum security wants less algebraic assumptions. And we don't care about prover time. We mostly care about reducing algebraic assumptions first and then dealing with the other scaling problems later. But I inherently think that the way our systems are right now built, most of them use trusted setups or have not even pivoted towards optimizing Starks. So if you're still using Starks right now, that means when I am saying I need to be ready for 2030, I need to think about redesigning my complete circuit layer, my hardwares, my protocol layer, my commitment schemes, and then I need to think about scaling, right? Hardware costs, computation. Can I even scale it for my users? How many users am I talking about? So my key takeaway from this panel and this talk is that first, let's focus on reducing algebraic assumptions because they're going to be the foundation for post-quantum security.
All right, guys. Well, with every good conversation, 30 minutes always goes really fast. So we're here at the end of our time. I just want to hear if anybody has any ideas that they want to share on, like, what does the post-quantum world look like, and only optimistic perspectives only.
I'll be quick. Bigger hardware means we can use fatter curves. Fat is not a technical term. Fatter curves that are post-quantum more efficiently, handle bigger proof sizes. And in theory, we just need bigger, fatter hardware to an nth degree. And that'll help a lot. It'll be a cat and mouse game, but the hardware is also a cat and mouse game. So I'm optimistic that we'll be fine. Not all blockchains will be fine. Those that adapt with fatter curves. Also, since we're at an improv show, I'll end with one more dad joke. FTX wasn't actually insolvent. They were in a superposition of solvent and insolvent. And once observed by an auditor, that's when we realized they were insolvent.
Yeah.
I actually think it's not going to look too different from, it's going to be there's going to be some increases in sizes. Some schemes will become obsolete. New schemes will be developed. I think the pain is in a transition period, but once the transition is done and the protocols adopt and all that stuff, I don't think it's going to look that there's no fundamental differences between what can be done now and what can do in the post-quantum world. I think we have all the tools. It's just implementing these tools for existing systems is going to take a little bit of pain.
All right. Well, if we don't have any other comments, that's the conclusion of this panel. And if any questions from the audience?
Hey guys, banger for panel, really enjoyed it. So my impression is that there's a lot of productionized, sort of mature deployments of MPC, TE, ZK, right? But with FHE, I think the production deployments are now coming, and there'll be more in the coming months and years. So are there opportunities for quantum security with FHE, and are there any mitigations possible that make any future FHE deployments more quantum secure?
Thank you.
So maybe one thing to kind of caveat my answer with, I don't know if people kind of follow standardization for post-quantum cryptography. Basically, that's put out by NIST, and that really determines what cryptography enterprises will have to transition to. And so far, the winners of that competition has been hash-based cryptography, which is utilized in Starks, for example, as well as lattice-based cryptography, which is what FHE is already based on. So FHE today is post-quantum based on the hardness assumptions it uses. Another interesting thing, if people want to keep an eye on it, so the same way NIST standardized some key encapsulation mechanisms and signature schemes for post-quantum stuff, they are also working to standardize threshold cryptography. So you can go online, follow that today, and there are people working both on threshold signing, ZK, as well as threshold FHE, which makes use of MPC and FHE as well.
Any other questions? All right. Well, that concludes our panel. Thank you guys for coming. There's some really awesome food within a couple blocks from here. It's lunchtime, and we are going to have our next panel at 1 o'clock, all about privacy in the post-quantum world. So hope to see you guys all back here, and looking forward to another great panel. So thank you.